All right, so let's put everything together that we've been talking of for phase separation problems and complete our mathematical formulation. Where we need to start in order to do this is to essentially go back and redefine the chemical potential, or recompute the chemical potential. Okay, so we do this now. This is what we need to do, okay? Remember how we got the chemical potential, right? We said that the chemical potential, mu, in order to get this chemical potential, all right, to get mu, what we did was the following, right? We defined the Gibbs free energy, G, is the total I think we'll just call it the free energy. It's the total free energy. It's the total free energy okay? And the way it is written, G, which is a functional of the concentration, and it is the integral over omega, okay? It is the integral over omega of our free energy per unit volume as we defined before, okay? Integrated over the volume, right? This is how we wrote it before, okay? This dV. Now we have something else. We need to include the effect of our concentration gradient based representation of the interfacial free energy. Okay? This is what we have. Okay? And then, right, we're going to work with this. Remember that in general, in order to have phase separation, this part of the free energy on which I've drawn an arrow must have a non-convex form. Okay? And just to remind ourselves of what that means, I'm going to draw a little thumbnail here. And remind ourselves that it has to have this form. Okay? All right? Okay, and then we have this additional component here, which is the representation of our interfacial free energy using the idea of concentration gradients, which we observed in the previous segment. Okay, now from here we do everything just as before. We take variations. We define C epsilon as C plus epsilon W, where C belongs to the same old space S, which is characterized by the fact that it contains all concentration fields C, such that C equals C bar on the concentration boundary, right? Alternately called the Dirichlet boundary or the essential boundary. Epsilon is a scalar. W, the variation, belongs to the space V, which consists of all functions W, such that W vanishes on the concentration boundary or the Dirichlet boundary or the essential boundary. Okay? Okay, so this is what we have, all right? And now our variational derivative. is delta G delta C, which is dd epsilon of G evaluated at C sub epsilon. Take that derivative and set epsilon equals 0. Okay, this is how we've rigorously defined our variational derivative. Okay. All right, so we're going to take that little, we're going to carry out that little computation. So what we're talking of doing now is dd epsilon of G C sub epsilon, and then setting epsilon equals 0 implies that we need to compute dd epsilon of integral over omega of chi function of C plus epsilon w plus 1/2 gradient of C plus epsilon w dotted with k, our tensor, which represents this interfacial free energy in the presence of concentration gradients, right? Acting on grad C plus epsilon w. dV. Now, remember, we decided to make life easier for ourselves by saying that the configuration omega is not evolving with the deformation, so we don't have this picture here, right? We do not have deformation and motion. The configuration is fixed in space, right? And it's over this configuration that we have phase transformation happening. I think you can see a little white spot, right, or a brightly colored spot. So just imagine that that is one of our phases of beta growing, okay? And as the concentration changes from blue to white across that, there is a free energy stored because of that change in concentration, because of that concentration gradient, okay? That's the sort of thing we're trying to represent. So imagine that that spot is trying to grow. I don't know if you can see it, but there are other small spots around here. Anyway, okay. So that's the setting we have here. Okay, so remember how all of this works out, right? So the first steps are fairly straightforward. What we get is that we observe that we're able to take that derivative with respect to epsilon inside the integral, right? And for the first term, we get, as before, derivative of chi with respect to C, evaluated at C epsilon, okay? Times derivative of derivative with respect to epsilon of C plus epsilon w, okay? And here, because the next term here is quadratic, right? It's quadratic in C plus epsilon w, or it's quadratic in the gradient of C plus epsilon w, okay? So we know that because of that fact, the way this works out is we get two terms, right? One is the following. In the first case, we get derivative, 1/2 epsilon gradient of w. Sorry, we lose the epsilon because of the derivative with respect to epsilon, right? So 1/2 gradient w dot k gradient of C plus epsilon w plus 1/2 gradient of C plus epsilon w dotted with k, now acting on gradient w, okay? Right, and this is just a matter of taking derivatives with respect to epsilon and observing that epsilon shows up here as well as there. Okay, so we have all of this. dv, and then once we take those derivatives, we need to set epsilon equals 0. Okay, let me write that more clearly. It got stuck at the very end of that slide, so let me set that here. Okay, straightforward enough, right? So now we know that because we're setting epsilon equals to 0, C epsilon falls back to C. Okay, whereas all these epsilons disappear. That epsilon disappears, sorry, that epsilon is set to 0. Okay, so when we do this, we get the following. We get integral over omega, we get chi prime, which is just derivative of chi with respect to C, it's that term, all right, times w from here, okay, and on the next term we get, if you look at how things work out in the next term, we get 1/2 gradient w dotted with k gradient C plus 1/2 gradient C dotted with k gradient w dv. Now, it is typical to also use a tensor k which is symmetric. Okay? As a result, because of the property of symmetric tensors, this thing reduces to integral over omega chi prime w plus, both these terms turn out to be the same then if k is symmetric. Okay, if k is a symmetric positive definite tensor, and we essentially get back here, we will choose to write this formulation as those two terms we can combine to writing as k grad C. Okay, k is a tensor, it's acting on grad C, gives us a vector, that dotted with grad w. Okay, so that is the variational derivative. Now, what we want to do with this variational derivative is isolate the chemical potential. Okay, now, and we isolate this chemical potential by carrying out the usual sort of arguments, the variational arguments on W. But in order to do that, we need to do one more step, which is we need to get rid of the gradient on W here. Okay, so what we are going to do is integrate by parts. Okay, so that tells us then that dd epsilon of G evaluated at C epsilon with epsilon equals 0, this is our variational derivative, is now integral over omega chi prime W, right? That term remains the same, nothing happens to it, okay? But for the next term, here's what happens. We get minus divergence of k grad C, okay, all of this integrated over dv plus integral over the boundary of the domain, okay, of k grad C, okay, dotted with n with w multiplying it here, okay, d little a. And this also comes about, that use of the chain rule, that application of integration by parts that we've carried out here. As I said before, in the context of variational derivatives on our nonlinear elasticity formulation, right? It comes about by a combination of the product rule, and the Gauss divergence theorem. Okay, we've done that a couple of times, so I'm not going to repeat it. I'll just remind ourselves here that it comes from, I'll just say that integration by parts is equivalent to the product rule of differentiation and the Gauss divergence theorem. And that's how we get that final result. And it's probably even easier, even more clear if you try to do that using coordinate notation. All right? So here we are. Oh, I just realized that, yeah, I'm missing a term out here, which, yeah, it's a good thing I noticed it. It's, I have here a W. Okay? So, what we get now is an integral over omega of chi prime minus, now, divergence of k grad C is, well, let's just leave it as that. Okay, we'll just leave it as that. So all of that times W. What I would have otherwise said is that if k were uniform, if k were independent of position, this divergence would come through to the gradient here, and that would become a del square operator. Okay, but we'll just leave it in this form. Okay, we have this plus integral over partial omega W times k grad C dot n dA. Okay, now the way we go ahead from here is the following. When we introduce the chemical potential, okay, we had the chemical potential, we'd identified the chemical potential to be the component multiplying W, okay, after integration by parts. That is mu. Okay? Now, what we say is the following. We say that the equilibrium conditions are obtained when this variational derivative that we have set up here is equal to 0. Okay, and this goes back to the way we originally defined equilibrium as an extremization of free energy. Okay, and the setting the whole thing to 0 is that extremization. Now, when we say that all the integrals that we have on the right-hand side here, we say that all of this has to be equal to 0 for all W belonging to V. Okay? We invoke the same variational arguments that we did before. Remember how we said that if W, if it has to hold for all W belonging to V, it also holds for certain special cases of W, right? And using those special cases of W, we concluded that at equilibrium, we say that mu, which is chi prime minus divergence of k grad C, right? We say that this quantity is equal to 0, and a very important additional condition for equilibrium is now the boundary condition. I'm going to go back a slide just to point out where the boundary condition comes from. We have this additional term in our variational derivative. We have a term on the boundary. And this comes about only because we've introduced this interfacial free energy by accounting for concentration gradients. Okay, so this is a very important term in the to understand the equilibrium case. This term must also vanish for equilibrium, okay, because the sum of these two has to vanish. And if this has to hold for all W, okay, belonging to V, it must turn out that each of these integrals should vanish, the volumetric integral and the surface integral. Okay? So the requirement that the volumetric integral vanish is that mu equals 0, right? And that we've already written on the next slide. The requirement that the surface integral also vanish is the requirement that K grad C, the whole thing dotted with n, should be equal to 0 on partial of omega. Okay? All right. Far from equilibrium, however, right, which is the case of interest to us, because we know that if the chemical potential is equal to 0, right, we know that if this were the case, we would see that grad mu equals 0 if mu were 0 everywhere, okay, and then there would be no flux. Okay, so no flux, nothing moving, nothing of interest, equilibrium case. We're interested in problems far from equilibrium, where the phase where that phase separation is continuing to evolve. Okay, so far from equilibrium. Okay, we say that once again the flux is minus m grad mu when well, we don't really need to say when, but we have this where mu is not equal to 0 everywhere. Okay, so this gives us the flux. Okay, all right. Now we just put all of this back into our mass transport problem, because our mass transport problem now is the following. Our partial differential equation for mass transport is the following. It is that the partial of c with respect to time equals our source pi minus the divergence of j. Okay?